Hi, the purpose of this video is to introduce you to how to simplify square roots, how to write them in the most simplest form. And so I'm going to interchange between the terms square root and radical. So try not to get too confused when I do that. But I wanted to first explain what radical is. So radical is basically that symbol, it's the radical symbol. And when there's no number there, so you'll see occasionally a number right here in the corner, like you'll see a 3 or you'll see a 2. That will mean different roots. A 2 means the same thing as if there was nothing there. Okay, but without anything, it's just square root. And a radicand is when there's a number in the square root symbol. That's called a radicand. And that is what we're going to be kind of focusing on today, what the different numbers that you would have as a radicand under the square root symbol. Okay, so when I say radicand, I'm just talking about the number. Okay, so product property. The first type is a product property, and that says when you have a product underneath a radical, then you can split that product into two different factors, each one with its own radical symbol. And this is, let me just give you an example of how this would work. So if we have, for example, the square root of 16, that would be the product of two numbers, 4 and 4. So we can rewrite this as the square root of 4 times the square root of 4. And we all know that the square root of 4 is 2, so this would be 2 times 2, which is 4. So the square root of 16 is 4. So this is an overcomplicated way of just explaining how that property works, how we can split a product into two different factors and keeping a radical around each factor. But we also know that 16 is 8 times 2, so we can also split it this way. Square root of 8 times the square root of 2, which is the square root of 16. And when you multiply the square root of 8 times the square root of 2 using a calculator, you'll see that it's still 4. And you can check it if you want, but it's, trust me. So that's how that works. Then we have quotient property saying when the radical is a quotient, when the radicand is a fraction. So if I have the square root of a over b, then I can split the numerator from the denominator, each with its own radical. Okay, kind of similar to the property using products, but instead of multiplying, now I'm dividing. So square root of a divided by the square root of b. Now let me show you how this would work. So just to try to explain it, so I have 5/6, and I'm going to multiply it by 5/6. In other words, I'm going to square it, and I'm going to get 5/6 squared. And we all know that 5/6 times 5/6 is 25 over 36. We just multiply straight across. Now, if we were to go in the reverse, we were to undo squaring it. That would be taking the square root of it. So if we want to take the square root of 25/36, then we know that it would equal 5/6 because we squared 5/6 to get 25/36. So to go backwards and take the square root, that's what we would get. And 5/6, 5 is the square root of 25. 6 is the square root of 36. So that's how that would work. So that's how you can take a quotient as a radicand and break it into two different radicals in a quotient. All right, so let's look at, there's three rules when you're simplifying radicals that you have to abide by. Okay, and one of them is when you're finding factors. Okay, this would be a product property. When you're finding factors, you can't have any factors under a radical that are perfect squares if you're going to simplify it. So you might want to know what perfect squares are. Perfect squares are numbers that are products of a number times itself. Okay, 16 is 4 squared, 25 is 5 squared, 36 is 6 squared, and so on. So that's why we call those numbers, those products, we call them perfect squares. So if we have the square root of 12, and we want to simplify that, we know that it has to be simplified because it has factors. one of those factors, we're going to see if it's a perfect square. Well, we know that the square root of 12 is the square root of 2 times the square root of 6, based on that last property, or the first one. But neither of these are perfect squares. But you could try different ones to see if you do have a perfect square factor, and in fact we do. So the square root of 4 is 2. So we can call this 2 times the square root of 3. Now this is relatively easy if you know that you have a perfect square factor. But what if you don't know, you're not sure that you have a perfect square factor? So I'm going to show you what you can do. Okay, but remember first that when you have a number times a radical, we kind of treat them the same way that we would treat a variable term. Notice that I don't have a multiplication symbol there. So this is how we would write it, 2 times the square root of 3. Okay, so let's say we have the square root of 12 and we don't know what the if it has a square root in it. Okay, we'll pretend we don't know. We already know the answer to this. So we can make a factor tree. So let me show you how to make a factor tree. Kind of the same way you do prime factorization. So we come up with two factors that equal 12 when you multiply them. But since we know the property, we can find two square roots that equal the square root of 12. And that would be the square root of 2 times the square root of 6. Okay, now the square root of 2 can't go any lower. That's a prime number 2. And so we can break down 6. That's the square root of 2 times the square root of 3. Now we've gone as far as we can go with prime factorization, so we look at what we have. We have the square root of 2 times the square root of 2 times the square root of 3. And when we write that out like factors, we can see that we have the square root of 2 times the square root of 2. Now this brings out a point that when you have the square root of a number multiplied by itself, it's equal to the radicand. Okay, so when you think about it, if you take the square root of 10, I'm sorry, the square root of 100 times the square root of 100, that's basically 10 times 10, and it equals 100. So we're looking for the two radicals that are identical. Okay, they're both factors and they're identical. That means we can pair them up and basically remove that radical symbol. Okay, so the square root of 2 times the square root of 2 is 2. And so that's how you use the factor tree. But let's say you have a number like 96 and you know you're not sure that if you have a perfect square factor. So this is where the factor tree would be really useful. So let's break it up. Now I would break it up by the simplest number I can think of, and since 96 is an even number, I know for sure it goes into 2. So this would be 2 times 48. And then 48. I think I see a perfect square in 48, but I'm not sure if it's the largest one, so I'm going to keep going. So I'm going to factor it down to square root of 2 times the square root of 24. And I see 24, that has a perfect square. Still not sure if it's the largest, so let me see. I'm going to break it down into the square root of 2 times the square root of 12, and then 12 goes down to the square root of 2 times the square root of 6, and so on. So here's what I have as my prime factorization. So let's see if we can pair any of these radicals and get rid of the symbol. Okay, so first I have square root of 2 times square root of 2. Those are paired up, and those become 2. Then I have another pair, so that'll give me 2 times 2. And that last two radicals, those are not pairs, so I can't remove those from the radical symbol. That remains the square root of 2 times the square root of 3, which is the square root of 6, cannot be simplified. So I combine my 2 and my 2, and that will give me 4 times the square root of 6. Okay, and again, I write it without the multiplication symbols, treat it like a variable term. So this is how the factor tree can be helpful with larger numbers. So let's look at the quotient property, and our second rule of simplifying is you can't have any fractions under the radical symbol. So you can't have a fraction as a radicand. So if you look at the square root of 13 over 100, we're going to use that property and split up the numerator and the denominator. And that'll give us the square root of 13 over 100. And we know that the square root of 100 is a whole number. So we're going to simplify it to the square root of 13 over 10, because 100, the square root of 100 is 10. Okay, so that's how you would simplify that one. Okay, and my third rule says you can't have any radicals in the denominator. So in the previous problem, we had the square root of 100, but once we rewrote that as 10, we can see that we're abiding by that third rule, which we didn't know at the time, but it worked out. Now let's look at one where it doesn't work so nice and pretty. So we have 5 divided by the square root of 7. Now we're going to use an old property that we might not have used in a while, and that is the identity property. We're going to write an equivalent fraction, but in order to write an equivalent fraction, we have to multiply the numerator and the denominator by something. And in this case, it would be this denominator. So if I multiply the square root of 7 times the square root of 7, I know that I'm going to get 7. So that will get rid of my radical in the denominator. But in order to make it an equivalent fraction, I got to do the same thing to the top and the bottom. And in my class, we call that the giant 1. Whenever you multiply a fraction by a giant 1, could be any number over itself, it's going to be an equivalent fraction. And in this case, multiplying by that giant 1 gets rid of my radical in the denominator. So I have on the top 5 radical 7, or 5 times the square root of 7, divided by 7. And now this fraction is completely simplified. Okay, so that's rule number 3, is you can't have that radical remaining in the denominator. Okay, so let's look at some examples where you have a variable in it. So the square root of 3b, just because this has a variable doesn't mean I'm going to treat it any differently. So I'm going to use the giant 1, but I need to get rid of this radical symbol here. I would multiply by the square root of 3b. Do the same thing to the top, and I know that the square root of 3b times the square root of 3b is 3b. Okay, and then on the top, square root of 2 times the square root of 3 times the square root of b is just going to be the square root of 6b. Okay, because we can break this off into the square root of 3 times the square root of b. And then, since none of them are replicas of each other, we don't have any square root of 2 times the square root of 2 or square root of 3 times square root of 3. We're going to have to put them all under the radical. Okay, so that would be the simplified form of this one. So let's try an example. So where we would use this in this expression with two terms, we have 5 times the square root of 3 plus the square root of 48. Now, in order to add these, like I said before, we can treat them like variables, but only if they have the same variable, so they wouldn't be like terms. So in this case, this has radical 3, this does not, so I can't just combine those two. So let's see if we can simplify them. So first we have 5 times the square root of 3. Square root of 3 is simplified. I don't have any factors here. That's a prime number. So this is already simplified. Square root of 48 can be simplified because there's a perfect square factor. So you can use a tree, or you can use a calculator, but 16 times 3 is 48. So this can be broken down as the square root of 16 times the square root of 3. You can use a factor tree to get that also. So whichever method you use, you're still going to get the same answer. So now we have 5 times the square root of 3 plus 16 times the square root of 3. And then the square root of 16 we know is 4. So 5 times the square root of 3 plus 4 times the square root of 3. And since they both have the same radical term, kind of like the same variable term, we can just combine the coefficients. 5 times the square root of 3 plus 4 times the square root of 3 equals 9 times the square root of 3. So that's how they work when they're in an expression using addition or subtraction. So subtraction, you would do the same thing. Just make sure that they have the same radical part. Okay, so let's try one using division. So the quotient, we have 21 sixths, the square root of 21 sixths. So let's go ahead and split those two, and that'll give you the square root of 21 over the square root of 6. And since we can't have this radical in the denominator, we're going to need to multiply the top and the bottom by the square root of 6. Okay, then we can look at the top. So on the top part, I'm going to have a pretty big number, so I'm going to start breaking it up at this point. I'm going to break up the square root of 21, and I'm going to call that the square root of 7 times the square root of 3. And then I'm going to call the square root of 6 the square root of 3 times the square root of 2. And so this allows me to see those pairs that are going to really help me out in the end. And then on the bottom, I'm going to have the square root of 6 times the square root of 6 is 6. So I can combine those square root of 3's. So the square root of 7 stays the same. Square root of 3 times the square root of 3 is 3. And then I multiply by the square root of 2 and put it over 6. So now when I'm going to write my final answer, I need to see if I can simplify anything here. That's the square root of 7 is prime, square root of 2 is prime, so I'm going to need to combine those. But let's look at those whole numbers. 3 and 6. That reduces to 1/2. So this will become a 1, and that would become a 2. Those properties still apply. Okay, so as my final answer, square root of 7 times 1 times the square root of 2 is the square root of 14. And then 2 is my denominator. So try those problems again if you would like, and go over them slowly, try to work them out, pause the video, and hopefully this helped. Thank you.